Hey guys, the previous video ended with this problem right here. So I told you to try this before watching the second video. So let's see if you did it right. Okay, so first thing I'd want to do is I'd want to solve each one of these independently of the other one. So if I start out with 2x minus y less than or equal to 10, I would want to subtract 2x from both sides. So on the left-hand side, I'm going to have negative y less than or equal to negative 2x plus 10. Now, I'd want to multiply both sides by negative 1 because I don't want negative y, I want positive y. Now, remember, when we multiply inequality by negative or divide by negative, we have to change the sign. So, guys, instead of less than or equal, we're going to get greater than or equal. And multiplying the negative 1 through the entire right side, we get 2x minus 10. So guys, that's one of them that we're going to need to graph. Okay, now the next one that we have is x plus 2y less than or equal to 8. So I'd want to subtract x from both sides. So this is going to give me 2y less than or equal to negative x plus 8. Need to divide every term by 2, which is ultimately going to give me y less than or equal. And guys, we don't have to change the sign here because let me get a cup of coffee here. So we have minus 1/2 x plus 4. So again, we don't change the sign there because we didn't multiply or divide by a negative number. So what we need to do now is we need to put these in, go to the calculator and put these in. So I've got that going right down here. So I need to go to y equals and clear out what I've done before. And what I like to do is I just like to put the equations in first. So I have 2x minus 10 and then the other equation was negative 1/2. So I need to put this in parentheses, so I have a negative 1 divided by 2 times x. Guys, always put your fractions in parentheses. And plus 4. Now what I'm going to do is I'm going to go over to the left and I'm going to set the inequalities the way that I need them. Okay, so this one needs to be less than or equal to, so I'm going to hit the enter button and I'm just going to scroll through the options. That's greater than, and that one's less than, so that's what I need. Now I'm going to hit the up button and go to the other one. I'm going to scroll through it until I find the greater than. And there it is. Now, what I'm going to do here is I'm going to choose something called Zoom Standard. In Zoom Standard, if you hit the Zoom button, it's the 6th option on my calculator, and it probably will be on your calculator too. So if I hit the number 6, it's going to choose this to be graphed over from negative 10 to positive 10 and so on and so forth. Now, you know, if you're doing this in class for a quiz or something and you're asked to do the solution, you know, how would you do that? Well, what you would want to do is you would want to draw your lines kind of similar to what you see. And I'm trying to do this over on the blackboard on Dosary. And you just shade in the regions kind of like they look. And making sure that the solution region is, you know, the darkest. Okay? Now, It looks like that the point 0, 0, where I'm circling right now, is in the checkered region. That's where the lines, or I'm sorry, the areas overlap, which gives us our solution to the system. So it looks like the point 0, 0, and there's infinitely many points here, but let's just choose one that's simple. The point 0, 0 would be a solution to our system of linear inequalities. So if I go back to the blackboard, you'll see what I've done here. Nothing fancy, but I want to focus on this point right here, 0, 0. So guys, if we go back to our original problem, which is this right here, and if we put 0 and 0 in for this, 0 is clearly less than 10. So that checks. And if we put 0 in for x and 0 in for y, 0 is certainly less than or equal to 8. Now, if we chose a number out in here, that's not going to solve either one of them. This would solve one equation but not the other. This would solve the other equation but not the other one. These points right here solve both equations, and this is our solution set. So the way you would solve your solution is you would draw a graph something like this. Now let's mix it up a little bit here, and let me show you where we're actually going to be headed. Let's go back to this problem, and let's put a spin on this. So let's keep the 2x minus y less than or equal to 10. Okay, let me erase that out. So this is going to be an addition to this problem that we're going to need as we get into linear programming. And let's go x plus 2y less than or equal to 8. Okay? But let's add a little bit to this. What if I came in and did this? Now, just so there's no confusion, guys, depending on the mood I'm in, depending on what your textbook is all about, because I choose problems on my math lab from different textbooks. This is equivalent notation. This is saying the same thing as this over here. This pair is saying the same thing as this. So you're going to see both notations. But anyway, what's this really telling us? Now, guys, this is an applied business math class. So we're ultimately going to take these types of problems and take them into linear programming, which is going to deal with quantity and cost and so on and so forth. So if you think about x and y being things that you may produce, it would seem natural in a class of this nature to put the restriction that they can't be negative. If we're doing golf clubs and golf balls, well, we can't have negative golf balls and golf clubs. If we're creating Chevrolet minivans and Chevrolet trucks, obviously those would be positive. So how would things change if we put this restriction? Well, the way it changes is this. Instead of looking at our graph from negative infinity, or really from negative 10 to positive 10, we would only be interested in the solution up here. We're only interested in the situations where x and y are both positive. So let's go back to the graphing calculator and see if we can make heads or tails out of this. So if we go back to the graphing calculator and look at what we've got, and we're only interested in positive, then we're going to have to come in and adjust the window. First of all, for the x-min, we don't need anything negative, so we'll start that at 0. And for the y-min, we don't want to consider anything negative, so we'll start that at 0. Come in again and look at the graph. So the solution part that we're concerned with is this part right here, the part that is checked. So that's an added restriction that we're going to see in these linear programming problems that we're going to have to deal with. And actually, in many ways, it makes the problems easier to do so. All right, guys, let's get to it. I told you this is all about linear programming. Let me tell you what a linear programming problem consists of. All right, the first thing it consists of is what we call an objective function. And the objective function is something that we want to minimize or maximize subject to certain constraints. So we usually let our objective function be given as z, and then when we read the problem, we're going to be trying to minimize or maximize something subject to certain things given in the problem. For example, we may want to minimize cost. We may want to maximize revenue, subject to certain things. Okay. The second thing that we always end up with are the constraints. And I always start the constraints with ST, which is just subject to, and what the constraints will be inequalities, just as we've done. So the graphing of the inequalities gives us a region that's pretty important to us, but it specifies the constraints under which or over which we're going to find the minimum or maximum to a particular function. Now, guys, this sounds hard, and it's a little bit more confusing, but just bear with me, okay? Now, what we do is we start with the constraints, and we end up getting something, let's say, that looks like this. So we graph our inequalities, and we turn out that we get a solution that is this area right here. Guys, we call this the feasible solution. I'm sorry, not the feasible solution, the feasible region. There's a fundamental theorem of linear programming. And the fundamental theorem of linear programming says that the solution to the linear programming problem must exist at one of these points. Now, guys, obviously this point is not interesting to us because that's just 0, 0. So we produce nothing, we do nothing. A lot of people like to do nothing, but we like to create stuff and quantities and minimize cost and so on and so forth. So again, we map our constraints, we find our feasible region. We have to find the corner points of the feasible region. That's the tricky part on the calculator, kind of. And then our optimal or minimal value for the objective function that we're maximizing or minimizing must occur at one of those points. So, gang, are we confused yet? Hopefully not. All right, I think the best thing to do is let's just get our hands dirty and just work a problem. So what I've done here is I've gone in and pulled out a couple of problems from a textbook. I don't think it's a textbook that we use. I usually don't like to use examples from the textbook because you guys can open those up, or you can take a look at those on your own. Well, maybe this thing will open sometime today. All right, there we go. So give me an idea of what's going on. I've got two examples, and I'm going to work those with you, okay? If my computer doesn't lock up on me. Okay, anyway, the first example says a manufacturer of lightweight mountain tents makes a standard model and an expedition model. Now, just like I do in systems of linear equations, I want to go to the last line, last sentence, and read backwards. So if I go to the last sentence here, it says if the company makes a profit of $50 on the standard tent and $80 on the expedition tent, and how many tents of each type should be manufactured each day to maximize the daily profit. So guys, right off the bat, I know that my objective function is going to be a function of how many units of each tent that I sell. So the first thing I'm going to do is I'm going to set X to be the number of standard tents, and I'm going to set Y to be equal to the number of what they call them, expedition. Yeah. Okay, so let me show you what I'm doing over here. I just set this up, okay? Now, I go back to my problem and I want to find out what I'm trying to minimize or maximize. Well, I'm trying to maximize profit. And the profit on each one of these is $50 and $80. So my objective function is going to look like this. I'm going to maximize Z, $50 on the standard tent and $80 on the expedition tent. So guys, this is the first important part of my linear programming problem. Now the next thing I have to do is I have to come in and read the problem, and I've got to identify the constraints. Alright, so let's do that. So the manufacturer, so what's going on here? We've got each tent, that should be standard tent. Let me put a T there. That'll drive me crazy. So each standard tent requires 1 hour from the cutting. Let's just concentrate on cutting right now. So 1 hour from the cutting for the standard tent, 2 hours from the cutting for the expedition tent. So it should make sense that we're going to have X plus 2Y. So the total amount of cutting time, and let's come down and see what so the maximum labor hours available per day in cutting is 32. So we know that the cutting time for the standard tent and the cutting time for the expedition tent, when we add those together, has to be less than or equal to 32. So to take care of that, I set the first constraint to be X plus Y less than or equal to 32. Guys, X is the total cutting for the standard. 2Y is the total cutting time for the expedition. Has to be less than or equal to 32. Now I go back to my problem and I try to find the next constraint, and I can see that I only have 84 hours for the assembly. Well, the standard tent requires 3 labor hours for each tent, so it should make sense that I'm going to have 3X. And the expedition requires 4 assembly, so it should make sense that I have 4Y, and I have 80. Whoa. I put down 80. It's not 80. It's 84. Okay, kind of makes sense. So guys, over here, what I've got now are the constraints. And again, should be pretty obvious that we are not able to produce negative number of tents. X is the number of standard tents. Y is the number of expedition tents. So guys, at the end of the day, what do we have? Our LP problem is this. It's the objective function Let me just double check, make sure I'm right on that. Yeah, 50x plus 80y. Subject to x plus 2y less than or equal to 32. Three x plus 4y less than or equal to 84. And we're producing tenths, so both of these have to be greater than or equal to 0. So guys, after all the dust settles, this is our linear programming problem. Now, the very first thing we have to do after setting up the LP problem is we have to get our feasible region. So this x plus 2y less than or equal to 32, we've got some work to do. So subtract x from both sides. Divide everything by 2. So there's one of the constraints that I'm going to put in the calculator. Okay? Let's go back to the other one. 3x plus 4y less than or equal to 84. Subtract 3x from both sides. Divide everything by 4. And let's see, 84 divided by 4 was that 21. Now, keeping in mind we have two additional constraints. Must be greater than or equal to 0. Okay? Now, guys, we can get a lot of information about our region we're going to graph these things over. Does anybody remember what these numbers right here are called? You better. It's called the intercept. So when I graph my my lines, I know that each one of these is going to have a y-intercept of 16 and 21. So when I graph these things, up here at 16, and it looks like that both of them have negative slopes, and up here at 21, you know, my lines are going to go something from there. So when I set my window, I'm probably going to want to set my y from about 0 to 25. So these are the things we've got to look at. We've got to look at where we're going to set our window to get our best picture of the feasible region. Now the x-intercept's a little tougher. And the way I do that is this left-hand side, I just try to imagine, you know, when y is 0, what would x be? And you can kind of think of this, if y is 0, and I solve this as an equation, you can probably see that that's 32. Now, I'm not going to use that in my linear programming problem or my linear programming solution, but I'm going to use that to get an indication of where I need to stop my x max. So I'm going to go over here and look at this one. So I've got 0 equals negative 3/4 x plus 21. So that's 3/4 x equal 21. Do a little bit of math there. Now I multiply by 4, which gives us 84 divided by 3. And this gives me about 28. Exactly 28. So keep that back in my mind. Because guys, sometimes we're going to have x and y intercepts in the thousands. So what am I going to set this at? I'm going to set this probably around 35, just something, you know, bigger than the biggest. Okay? All right. So let's go to the graphing calculator and put this information in. Okay? So I'm going to go to y equals. And I'm going to clear these things out. Alright, so the first one is negative 1/2. Put it in parentheses. Guys, if you want to use negative 0.5, that's fine. The next one is negative 3/4. I'm going to change it up a little bit here for those of you that prefer to use the decimals. I'm going to show you how that works. Now, I don't care if you use decimals if they work out, you know, exactly. But if you got something like 2/3, I don't want you to put in 0.6. I want you to put in 2/3. Now, what we need to do next is we need to come over here and get our inequalities. And both of these are less than or equal. So guys, we need to run through the options. It's greater than. It's less than. My computer's really slow, but I got a lot going on here. Okay, now I've got to come in and think about the window. Guys, a lot of students, I had a buddy one time, he said, I hate math. And I'm like, why? He said, it takes too long. Well, I guess. But, you know, to do it right, you just got to think about some things. So our x is the number of standard tenths. Well, it can't be negative, so we start at 0. And from looking at the x-intercepts, I can see that, wow, this computer's driving me insane, that I need to have something out around 35 to get the best picture. My y's are the number of expedition tenths. They can't be negative, so I started 0. And I saw from analyzing the y-intercepts that we should be at about 25. All right, gang, hit graph, and we're going to get our feasible region. And our feasible region is the intersection of the two lines. Now I'm going to get this written down on the screen. So give me a second here. I'm going to write this down. So it kind of comes in like that, and then it kind of goes down like this. And I'm going to exaggerate things, as I'll show you in a second. Okay, so ultimately this is our feasible region. So the fundamental theorem of linear programming says that the solution must occur at one of these points. Now, you got to think, this line went on up and this line went on out, but we're not using that. But we can use it to our advantage. Now, first of all, what about this point right here? And this is, hopefully you can see what I'm doing. I'm making it, it's the one that I'm making whiter. What is it? What is that ordered pair? Well, it's going to be 0, comma, whatever. Again, you got to think up here. There's another y-intercept up here. So which line has the lowest y-intercept? Well, that would have to be this one right here, the 16. So I know that point has to be 0, comma 16. What about this point right here? Well, that's going to have to be something 0, because it's an x-intercept. And if I go back to the x-intercepts that I set out earlier, which one does that have to be? Well, it has to be the smallest one. It has to be the 28. So this would have to be 28, comma 0. Now this one, we want to find the point of intersection. And it's a really important one, because as you'll find out, that's usually the solution to our LP problem. Not always, but it usually is. So we're going to need that. So guys, I'm going to show you a handy dandy little feature on your calculator that helps you find that point. So Again, computer's running really slow, but got a lot going on in the background. Now, guys, if you'll go second function and go up here to calc, you'll get this screen. And if you come down to number 5, it says intersect. So I'm going to choose 5. And I get, well, this computer's running so slow, it's annoying. So let's go second, calc, hit number 5. And it should take us to our graph. Now I know your calculator's working a lot quicker, but this thing takes up a tremendous amount of space. Alright, so what it's going to ask us first of all is to choose the first curve. Now here's a situation where I think it's easiest to go back into y equal and go over and take off the shading. I want to go back and just see lines because it's going to be a lot easier to visualize the feasible region if I just look at lines. So I'm going to put this back to the default. Okay, so you can see over here both are back to the default. Now I'm going to hit graph, and I know where my feasible region is. I don't need that anymore. I know, watch my cursor. I know it goes from here down to that point, and then it comes down here to this line, and then, you know, all this stuff in here, okay? So I need to find that point. So if I go second, calc, number 5, it's going to tell me to choose my first curve. Well, I've only got 2. Because you got to think, and we're going to have this. Sometimes we'll have 3 constraints, and we're going to have to tell the computer which 2 lines we're choosing. But for right now, we don't have to worry about that. So I'm just going to hit enter. It'll say, "What's your second curve?" Well, it's the only other ones, so I'm going to hit enter. The next thing it's going to do is ask us to guess. Now, when you've only got 2 lines, it doesn't matter, but you could have something that has multiple intersecting lines, and it wants you to take it to the one that you're trying to find the intersection of. So if I hit enter, it's going to do all the work, and it's going to come up and say intersection x equal 20, y equals 6. So guys, that's what I need. X equal 20, y equals 6. Alright, I've lost my... Alright, so this point right here was x equal 20 and y is equal to 6. Now, is that right? Yeah. Alright guys, what we do next is we have our final step. What I want you to do is set up a table something like this. And I want your x values, your y values, and then I want your z value. So our x and y's are 0 and 16, 20 and 6, and 28 and 0. Our objective function from way back when is 50x plus 80y. So guys, when we have 50 times 0 plus 80 times 16, we get 1280. When we get 50 times 20 plus 80 times 6, we get 1480. And for the final one, when we put in 28 for the x and 0 for the y, we get 1400. So let me write that out. 50 times 28 plus 80 times 0 is equal to 1400. Okay, so clearly the biggest number, and again we're trying to maximize here, so we're looking for the biggest number. The biggest number occurs at 1480, okay? And that occurs when we have 20 standard tenths and we have 6 expedition tenths. So the solution to our LP problem is we get a maximum revenue of 1480 when 20 standard tenths and 6 expedition tenths are produced. So guys, as you can tell, these are a little bit more involved. They take longer, and if you're somebody who's super impatient, well, you better learn to be patient for a couple of weeks, because that's about how long we'll spend on these types of problems. They take more work, and more work just means there's more places to make mistakes. So we've got to be careful at every single step. Guys, I'll tell you what's going to happen. You're going to find out that the first problem we work, the point of intersection is going to be the solution. You'll find out the second one, the third one, the fourth one probably. Most of them. Had a student last semester who said, well, it's always the intersection. I'm not going to check these other points. Well, guess what happened on the final exam? Up popped a kind of strange example where this point right here wasn't the solution. It was one of the x-intercepts or y-intercepts. And he missed it and actually took his grade down quite a bit. So we don't want that. Guys, just suck it up. It's going to take you maybe 2 minutes longer to do it right. So just go ahead and do it right. Okay? All right, let's work the next one really fast. If my okay, as you would expect in a business class, we might be talking about bonds. So an investor has $60,000 to invest in bonds of, actually that should be AAA and B qualities. The AAA gives a yield of 6% and bond B gives 10%. The investor requires that at least 3 times as much money should be invested in AAA bonds as in B bonds. Now that's going to be one we're going to have to think about, right? How much should be invested in each type of bond to maximize the return? All right, guys, so we know that right off the bat that our objective function is going to be z equal max something. I'm sorry, that's not true. It's going to be max z equal something. Well, if we're trying to maximize the return, we're going to take the amount in the AAA. So I'm going to let x equal amount in AAA, and I'm going to let y equal the amount in B. And my maximum return is going to be 0.06 times x plus 0.10 times y. Okay? So just let you show you what I've written down. This is the max function, and I've got to first of all identify what variables stand for what amount of bonds. Alright, so that's part of it. Alright, so now we've got to get into our constraints. Well, first thing it says the investor has $60,000 to invest. Doesn't mean he has to invest all of it, or she. So how much should he or she invest? Well, it's got to add up to less than or equal to $60,000. So one constraint's really simple. And that's this one right here. I'll tell you what, let me see if I can get something going here. Let's see if I can. I'm really, to be honest with you, I'm afraid to try anything with this computer right now because it's working so slow. All right, let's do that. And let's do this. All right, so we can get a little bit of split screen action going on here, okay? So back to the z equal. This is our objective function, and we've got to come in and find some constraints, okay? So it's pretty clear again. A person has $60,000 to invest. Now, the most confusing part of this is this constraint right here. The investor requires that at least 3 times the money should be invested in X as in Y. And let me show you what is so tempting. Let's see, 3 times as much money in X as in Y. Hold on just a second. Now, it's going to be tempting to write this. So at least says that the amount in X has to be greater than or equal to. It's kind of like if somebody's at least 6 foot tall. It means they're 6 foot tall or greater. So when we say that the amount in the AAA, which is our X, has to be 3 times, it's so tempting to write that. And guys, that's wrong. That's not what we want here. Remember, to make these things equal, we have to multiply the lower amount by 3. So this is the constraint that we would need here. Now let me get rid of all this and get it into form that makes sense. So we need X to be greater than or equal to 3Y. Guys, we're talking about money, so we want our money to be positive, right? Both amounts have to be greater than or equal to 0. So our linear programming problem is to maximize z equal 0.06 x plus 0.08 y, subject to $60,000 and I think it was x greater than or equal to 3y, and both quantities have to be positive. So that's our LP problem that we have to work. Okay? Now, first thing we'd want to do is we'd want to solve the first one. So the first one is going to be really easy to solve. Now let's think about it. We're going to need the intercepts, right? So guys, the x-intercept here from what I showed you to do a while ago is 60,000. The y-intercept is also 60,000. So I've got to make my window pretty big to make this problem work, right? Now my other function, x greater than or equal to 3y, I showed you a little trick back in video number 2 that says we can change the order. But when we do that, we have to change the inequality. Instead of reading from this way where the inequality is pointing toward the 3y, if we read this way, the inequality still has to point toward the 3y. Well guys, it'd be pretty clear we have to divide both sides by 3. So the other inequality will be y less than or equal to 1/3 x. Alright, so this is a kind of a cool situation in that the x and the y-intercepts are just 0. So let's go take a look at our graph. So guys, go to y equal. Let's clear out what we've got. The reason I make a deal of that I want you to clear everything out before starting is because I've seen students work problems where they have a constraint from a previous problem combined with another. So you know, we don't want that. So negative x plus 60,000, and you can eliminate or at least reduce the chance of that happening if you just start with a blank slate from the beginning. Okay? Alright, so the next one is y less than or equal to 1/3 x. So guys, we got a fraction here that we need to put in parentheses. Now we need to come over and set our inequalities. Now my slow computer is probably driving me crazy. Some of you probably like that because it's easier to stay up to date. So guys, we need less than, so let's run through this. So there's less than, and this one we need greater than. No. We need less than on both of them, don't we? Okay, now we got to set our window. So our window's a little bit different here, right? So we're going to run this thing not from 0 to 35,000, but I want to run it from 0 to 35, but I want to run it from 0 to 60,000. And I want to run this one from 0 to 60,000 as well. Okay, now I'm ready to graph. And this is what I get. Alright, so kind of a strange, not really strange, but you know, I'm going to call it a very interesting feasible region. And I'm going to do my best to replicate this. Alright, so if I go back to my screen, You can see what I've done here, and so here's our feasible region. Now, what's going to happen here is you're going to see that I want to make this bigger. All right, I need my points. Now, obviously this point is going to be 0, 0. Nothing too crazy about that. And guys, this one has to be 60,000. 0. For obvious reasons. Let me. So we need to find this one, and it's going to be easiest to let the calculator do that. So let's go back to the calculator. Just like before, we'll go second. Calc. Second. Calc. Number 5. First curve, hit enter. Second curve, hit enter. Our guess, we've only got one point of intersection, so there's no need to make a guess. Let the calculator figure it out. And the point of intersection there is 45,000 and 15,000. Alright, gang. Not going to need the calculator anymore, so I'm going to shut this down. Maybe that'll make my computer run a little better. And I really don't need that for a while. Alright, so let's get the screen here. Now what I need to do is I need to set up my table just like I did before. I need my X's, I need my Y's, and I need my Z's. So guys, from way back when, we're trying to maximize 0.06 plus 0.08y. And our points, guys, this one's irrelevant, the 0, 0. That's not something we need to consider. So 45,000, 15,000. And the other is 60,000 and 0. So you can see in each case they've got 60,000 invested, and the amount is X is at least 3 times what we have in Y. So guys, let's put it in. This would be 0.06 times 45. Yeah. I'm going to just kind of abbreviate here. 45,000 plus 0.08. Obviously, you don't put K in your calculator. So I'm going to grab my calculator and put this in. So we've got 0.06 times 45,000 plus 0.08 times 15,000. And it looks like to me that my total return here is 3,900. Now if I put 60,000, I put all of it in the first one. You can probably, your mental math can already tell you that it's going to be less, but if not, just go ahead and type it in there and make it happen. So it's going to be 36,000. How about 3,600? So guys, the best return we're going to get is at the 3,900. Okay? And that's going to be 45,000 in the first investment and 15,000 in the other. So guys, we've finally got our information to where we can go answer our problems. if my computer will allow me to do so. All right, so how much should be inversed? Oh gosh. All right, invested in each type of bond. So we need what, 45,000 in double A's, triple A's. Sounds like a battery, doesn't it? And we need 15,000 in bond B's. What was the maximum return? Well, that turned out to be $3,900.